Good morning and good afternoon to some of our friends who have joined from Europe. I'm going to talk about reducing prototype development cost by 50%, but I'm going to expand this a little bit more, where we talk not just about prototype development cost, but how our heavy machinery industry customers have leveraged MSC technology for meeting their business initiatives by addressing their technical challenges. So we will be covering not just prototype designs and product designs, but also manufacturing simulations and how it relates to savings and costs. So as some of you may know, MSC has been playing a vital role in product design process for many customers for more than 50 years. MSC Software was founded in 1963 after the famous JFK speech where he talked about ambition of America's ambition of putting man on the moon. And MSC played an important role in realizing that dream. MSC was contracted by NASA to develop this let me use a pointer to develop the NASTRAN, which stands for NASA Structural Analysis, in 1965. And since then, over the 50 years, we have not only developed, but also acquired a lot of key technologies to build a very rich simulation portfolio that has been helping our customers for more than 50 years. So let's look at some of our portfolio. With this rich portfolio, MSC's strategy has been helping our customers in simulating the entire product engineering process as well as manufacturing engineering process. So starting with materials, where you have there you have a choice of picking out materials. We have software that will help you to design complex multi-scale materials such as carbon fiber composites and other particulate composites to come up with the required specifications or required properties that go into your products. So starting with materials and then taking those materials into manufacturing. So we have various manufacturing processes such as joining and welding and forming and forging and so on. So we can do a lot of simulations of those to come up with the components or parts that go into our systems. So once we have designed those parts, there are critical things for parts such as doing stress analysis, deflections and fatigue life and vibrations and so on. So we can do all those types of analysis on individual components, and these individual components then go into assemblies and entire systems such as planes and cars and heavy equipment vehicles. So MSC's software portfolio basically addresses right from materials, choosing materials, to the entire system, not only in designing but also in manufacturing. So when we talk about heavy machinery industry, the three big industry segments that come to our mind are mining industry, construction industry, and farm equipment industry. But it is not just limited to that. A lot of technology which we are going to see now is extremely applicable and has been used by customers doing other things such as, for example, escalator makers and elevator makers and robotics and so on. So, so when we were looking at this industry and the challenges of the industry, we did a lot of research. We went through a lot of research publications, observed a lot of market trends, and also talked to our customers. And from that, we came up with certain strategic business initiatives that these companies in the heavy equipment machinery industry are dealing with. So high performance and autonomous vehicles is one of the major initiatives, where autonomous vehicles also kind of includes upsizing, because there has been some trend in farming for consolidation of farms. So they're moving towards larger equipment. So upsizing autonomous vehicles and high performance is some of the key initiatives that we are seeing in terms of trends. Also, reduction of warranty cost is always a very important initiative, as well as noise reduction, because a lot of this equipment is operating in environments that which is very a little bit noisy. So noise reduction is very key issue. Lightweighting of the materials has been a new and innovation initiative in aerospace and automotive industry. However, in the heavy machinery industry also we are seeing some adoption of this lightweighting for getting better performance. And with the foreign competition that our industry faces, cost-effective manufacturing is also another a very important initiative that these industries have. So let's look at some of these business initiatives and how they translate to the technology challenges which we can address. And once we address those technology challenges, we can meet those business initiatives. So when we talk about high performance and autonomous vehicles, designing of moving parts in the assemblies, because a lot of these equipments, they have moving parts, and that is a key issue. You have to study multi-body dynamics and control systems which are driving the motions of various components, and then structural strength, whether it's linear or non-linear, structural analysis, dynamic response of a vehicle in terms of its natural frequencies or frequency response and NVH and so on. Then there are safety issues. As you can imagine, a lot of this industry equipment is operating and picking up heavy loads. So safety is a very key issue. And there are durability considerations, fatigue calculations that need to be done. There are also regulations in terms of rollover protection systems and falling object protection systems and so on. So all impact in considerations also have to be taken into account. Then of course noise. There are noise regulations, ISO and European regulations for this equipment that is operating. A lot of this equipment is operating in construction equipment that you see on the road and in the neighborhoods. So there are very strict noise regulations, and the acoustics analysis must be done for that. And then cost-effective manufacturing, where we have various forming processes, joining processes for putting these components together or making the components and then making assemblies of these components. So all of these technology challenges basically translate to some sort of a business initiative that the company has. So let's see how we address those. We can group them into product design and manufacturing process design. So let's first talk about higher performance and autonomous vehicles. By better designs of moving parts and assemblies, here is an example of that. Let's look at the excavator dynamics. When loaded, when this thing picks up the load, there is displacement and flexing of certain parts that happens. That must be accounted for when you do multi-body dynamics analysis in order to capture the behavior accurately. On the right-hand side, it shows an animation of an excavator operation done using Adams. And here is a case study where the same excavator for a customer by name Daewoo, where mechanical dynamics of a swing, boom, and arm buckets were optimized using integration of Adams with Simulink, and the simulations helped to improve performance and optimize various structure shapes to reduce development time by 10% and shorten time cycle by 20%. Let's talk about multi-body dynamics and control systems and the integration of the two. It is very important that we are able to integrate the multi-body dynamics and various control systems such as EZ5, MATLAB, and so on. So if you look at let's look at the concept of both of these. So typically, a control system is best represented mathematically with a block diagram like this. And motion or a multi-body dynamics is best represented with geometries, and the way we study that is with animations and graphs and how the forces and the velocities and accelerations are for that part. So when we combine these two, basically here it shows an example of how EZ5, this control system is done in EZ5. This is basically a hydraulic and electrical control system that is done in EZ5, which is driving a special type of motor for this flap that opens. This is a flap this is an air brake from an aircraft. So using the integration of control system and the multi-body dynamics, we get much more accurate dynamic model of this flap. So this control system here is used, which is EZ5. However, it could be a MATLAB or it could be a Simulink or some other control system. So the mechanisms which are used in the multi-body dynamics, how they're driven by the control system, that can be integrated. Here is an example or a case study of Parker Hannifin, which used EZ5 for EZ5 thermal hydraulic library in combination with MSC Adams to reduce development time while increasing the power density of the hydrostatic pump for improving the performance. And here they achieved a reduction in development time and, of course, the cost related to that. Here's another example of integration of Adams controls. Here, because of the integration of the control system that is driving the motion, we get much more accurate representation of the system. Now, talking about the strength of the components that go into the system. So you may have various components that are in the system. Some of them might go through some linear stress. Some of them might be going through nonlinear stress. Some of them might be more complex materials such as rubber, seals and boots and so on, or bushings. So the way Adams deals with that is some of the bodies can be converted into flex bodies. So for example, here you are seeing one arm which is turned into a finite element model. So this is a flex body. So we can do Adams flex bodies in the Adams model. And these bodies can be linear, which will be done using Nastran, and they can be nonlinear, which will be done using MOL. So here is an example of using Adams and Mark co-simulation for getting an accurate representation of the system and the analysis of the flex body. Now let's talk about dynamics response and dynamic response of the vehicle and durability and fatigue. So when we're talking about dynamic response here, now we are not talking about multi-body dynamics, but we are rather talking about the natural frequencies and frequency response, NVH, and fatigue. So most of these equipments, as you know, are picking up heavy loads. So there are issues regarding vibration fatigue, crack propagation, and so on. So we have customers, they have used various types of fatigue analysis, whether it's a cap fatigue or fatigue of the wheels or some sort of crack propagation in a component. All of that can be done using Adams durability and MSC fatigue or natural embedded fatigue. So let's look at a couple of case studies. This is one of the case studies that was presented by Caterpillar at one of our conferences. They used Adams and Nastran for designing of electric rope shovel, and they designed this for higher fatigue life, and they basically reduced their development cycle significantly. This was presented by Caterpillar at one of our conferences in user conferences in 2013. In the next slide, you will see another one of our key customers, John Deere. On this 20-foot rotary cutter, they cut down the development time from 4 years to 2 years by setting up a virtual lab where this test that you see on the right-hand side that is done in the lab, the same test, they set it up in a virtual lab using Adams and MSC fatigue. Thus, they were able to reduce the development time from 4 years to 2 years, making a significant saving in the cost and time. One thing I want to point out here is not only that we have helped our customers reduce the number of prototypes and the amount of testing that they do in the lab, but we have done significant enhancements in doing the fatigue analysis itself. So typically the fatigue analysis is done in this manner, where you have finite element model, and then you do some sort of a stress analysis package, whether it's Nastran or Abacus or ANSYS or whatever, and then you take that stress results and into some other fatigue package. And doing in this process, as you know, the result files can be quite large, and so there is a lot of file management, and it's a very time-consuming process. So what MSC has done is they have taken the fatigue algorithm from MSC fatigue and put it into Nastran. So basically, you go from a finite element model straight to fatigue analysis. So when you're requesting stresses, you also request your fatigue results, which we call Nastran embedded fatigue. As you can see here, you can have time compression of the entire process by as much as 75%. So this is a very significant development that MSC has done, what we call Nastran embedded fatigue. So we are not only reducing number of tests that are done in the lab, but also the analysis itself is compressed significantly. Now let's talk about safety, because safety, as we said before, is a very, very key issue in this type of analysis. So let's ask ourselves, what about tip over? Is tip over a safety issue? Yeah, of course it is. In this case, it is not as critical, it doesn't seem to be as critical as this case. This is a very, very serious business. It's a very, very critical issue for not only the operator, but also people around who are working. So let's look at some of the statistics as far as the safety is concerned. So if you look at the fatal injuries in 2012, as you can expect, a lot of these injuries are in the construction and the transportation industry. So this safety is a very, very critical issue. Here is some more statistics on forklift safety. Amount of percentage of accidents by tipping over and running into each other and those kind of things. As you can see here, we actually helped one of our customers that we are not allowed to use the name here, so we are just showing a general animation. But this customer, we helped them to set up a virtual test lab that will do the stability analysis of the forklift and make sure that the forklifts that they're designing pass the ASME stability standard. And by doing so, we were able to reduce the cost of their R&D by 30%. What about acoustics? Acoustics is another very, very important issue. A lot of this equipment, as we said, is operating in neighborhoods and on the construction roads and things like that. So there are very strict acoustic standards. As you can see, acoustics regulations are getting much, much more stringent now. If you see here, in 1970, the acceptable dB levels were around 82 for certain vehicles. Now in year 2000, they have come down to 71, which means that the noise regulations are becoming much more stringent, and all the heavy equipment manufacturers have to comply by those. Now here, I'm going to use a pen here. So here is the ISO standard 7216, where you have a tractor in motion. So the tractor is moving from here along this line. And then you have two microphones which are placed 7.5 meters on either side of that line. And when the tractor is 10 meters away, that is 10 meters away here and 10 meters away here. So when it's approaching the microphone 10 meters away, and then it goes away outside 10-meter range, they record the noise levels. And as you can imagine, the noise level would go something like this. And this maximum noise that is allowed is about 89 dB for 1.5 more for a tractor that is more than 1.5 tons, and 85 for 1.5 tons or less. So these are the some of the standards. And the point here is basically the standards are becoming quite stringent, and one must address them using acoustics simulation. So we can do the Adams simulation coupled with ACTRAN, which is done for acoustic simulation. So here we are looking at various different types of noise. So there are interior noise and exterior noise. So here you have a cabin, and there is a cabin noise. So there are regulations for the safety of the operator who has to hear that noise. So there could be a cabin noise, or there could be an exterior noise such as engine noise, noise that is generated by the cooling fan or the exhaust noise, and so on. So ACTRAN can simulate various different types of noise sources and the propagation of these sources using various methodologies. For example, here in the cooling fan noise, we can get combine ACTRAN with CFD to predict the cooling fan noise, which is one of the major sources of noise in the heavy machinery industry. We can also predict the engine noise by combination of NASTRAN and Adams and ACTRAN. So here is an example of combination of multi-body dynamics and ACTRAN, where we have covered Adams along with ACTRAN for analyzing noise coming from complex moving mechanism such as a gear transmission case. So Adams will calculate here the multi-body dynamics and the structural vibrations, which will be then used by ACTRAN for doing the acoustics excitation, and then it will be able to calculate the noise. So Here is an example of Adams and Actran coupling for noise simulation of a transmission case, geotransmission case. Now when we come to manufacturing. So in manufacturing, we are, we have manufacturing processes such as forming, forging, heat treatment, and welding, and so on. Here is an example of a robot that is doing the welding. So the challenges in welding are basically related to distortions, excessive distortions and residual stresses, but also to reduce the number of amount of distortion. There are you might have to do various trials in terms of how do you constrain your parts which you are welding, and what is the weld sequence that is optimum to have least amount of distortions. So all of that is very time and cost consuming. So we have semi-fact welding, which has been used by a lot of our customers for optimizing the welding process, reducing the scrap, because if the weld quality is not good, then basically it's scrap. So semi-fact welding software will also give you residual stresses in the weld, the quality of the weld, and so on. The material and energy savings for optimizing the processes, and a lot of these distortions are taken are fixed after welding by what they call heat and beat method. This basically post-weld straightening, but it's really they heat it and beat it to make it come into the tolerance. And that is a very, very laborious and time-consuming process. So if you can come up with a best configuration for welding, which will give you the least distortion and least residual stresses, that will save a lot of cost and time. So semi-fact welding can do that for you. Here is an example of a simple part which has been welded, but as you can see here, as it is welded over here, you have a lot of distortion at the end here. It's about 2.8 millimeters of distortion at the tip here. But when we do a little bit of tack welding here, so in this case, we did a little tack weld here in the 4 corners, and then you can see that the maximum distortion is less than half a millimeter. So these type of what-if scenarios, so when you are doing welding an assembly, where should you tack weld? How should you constrain? Where should you have your fixtures? What is the best sequence? Should I go weld number 1, 5, 3, 4, 2, or 1, 2, 3, 4, 5? That kind of what-if trials can be done using welding simulation. Then comes another forming process, which is called self-riveting. In self-riveting is also a very, very time-consuming process, because the physical testing can take a lot of time. First of all, it requires special machines for testing. Then the specimen preparation time can be significant, and then of course you have to look at the micrograph to determine how the rivet quality is. So here it shows a micrograph, and there are certain parameters which are usually studied for the quality of the rivet. Here in the middle, you see the simulation of the self rivet, and here is actual micrograph. So here's a comparison of simulation and the actual physical rivet. And here on the right-hand side, you're seeing the same rivet in shear, how it is behaving in shear in terms of stresses and so on. So this is done using semi-fact self-riveting simulation. And here you see there are a lot of different manufacturing processes that semi-fact can simulate. Here you see cogging. Then you see forging. Forging is a very, very interesting process where you have metal that is heated up and then it goes through one or more stages of forging to come to the final product. Now, if we had a forging simulation, we can decide, do I need to have 3 stages of forging, or I can get away with 2, or do I need 4 or 3? What are the die and the tooling geometry that is required for each one of those stages? All of these what-if trials can be done using a simulation package such as Simulfact Forging. Here it shows sheet metal forming and rolling as well as ring rolling. So all of these different processes can be simulated using Simulfact, and they can be used for reducing your trials on the shop floor. The shop floor trials are not only expensive in terms of time, but they are actually preventing your machines from producing the parts that go out of the door. So basically, you have machine downtime because of this, and of course, all the labor that is required for making the trials and so on. So that is the cost in addition to actual tooling cost itself. So it's a very significant cost savings you can achieve here. Here you can see that various different types of processes that can be simulated using Simulfact. Various types of joining processes such as welding and self-riveting, the different types of metal forming processes, as well as forging and so on. But here what I want to point out is all of these processes can be chained. So this is a key point. A lot of these different processes, for example, if you make a part by forging and then some of these parts which are forged are welded together, all of those can be chained, and the importance of that is that history of the manufacturing process is carried over. So here is an example. So here you have a billet, here you have a simple billet, and then this little piece is cut out from that. That little piece is used as a self-rivet, in the self-riveting operation. So what happens is when you cut it, you already have some sort of some stresses in there which are carried over. So because of the chaining, you can actually carry those over. So there is a lot of emphasis on integrated computational materials engineering, ICME. This is what it is. Basically chaining so that we can carry over the history of that manufacturing process into our analysis of fatigue and so on. So I'm going to hurry up and just say that we have helped our customers. We don't have permission to specifically discuss their names, but they have reported to us that they have achieved cost reduction of as much as 50%. Because of the tool design, cost reduction in production as much as 10% or more, and better quality of as much as 15%. In summary, we can look at this, our excavator that we have been working, the motion of this excavator can be studied using atoms. Then some of these components can be made flexible, like this one, by making it a flex body in atoms, and done analysis using NASTRAN. Then the same can be passed on for doing fatigue analysis, and then this motion of this excavator can be driven by control system such as EZ5, and of course we can do ACTRAN for cabin noise and other types of noise. You can also integrate this with atoms with ACTRAN, and if there are any nonlinear components in there, we can do that as well. Any of these components which are manufactured, we can do that using the Simulfact welding and forming. So, with that, I'm about to wrap up here. So we started with these business initiatives. And these are the technology initiatives, technology challenges that will help us to meet this business initiative. And these are the MSC solutions, Adams, Nastran, Mark, Adams Mark co-simulation, durability, action, and SimIFACT. These are the MSC solutions that help us to achieve this business initiative. So if you look at a typical heavy machinery flow, you may have certain domains such as conceptual design, mechanical systems, and innovation, and various different types of analysis that you're doing in this product design phase, as well as in manufacturing process design. We can address a lot of these by our MSC tools such as Adams and Nastran and Digimat and Mark and SimIFACT. So with this, I'm going to conclude my presentation, and I will open it for any kind of questions.